Thank you. Let me first say thanks to the organizers. It's a real pleasure to be here and have this opportunity to teach this mini course. So yeah, sort of the goals of the course, the main goal here is to explore the world of groups acting on rooted trees. So we're going to have one example that's going to be our motivating example throughout the course. So motivating example. The Gregorczyk group. All right, this was a group introduced by Gregorczyk in the 80s, 1980. And it had, it really changed the way we think about a lot of, fundamental concepts in geometric group theory. So for instance, it changed the way we think about topics such as growth of groups, amenability, torsion, and a whole host of other properties. So in particular, when Gregorczyk introduced this group in the 80s, let's see, he said I can use these boards, yeah. So, right, when he introduced this group in the 80s, it turned out that, using these methods, so it turns out you can construct using simple automata I'm putting this word in quotes because we will define this probably on Wednesday. But using simple automata, we can build groups with complicated properties and structure. In particular, we're able to build these groups, that are really difficult to find otherwise using more geometric type technique. All right, so I will use gamma throughout the mini course to represent the Gregorczyk group. So properties of gamma. That we'll talk about here. So first of all, it has a solvable word problem. And even more than that, it's solvable in polynomial time. See, it is finitely generated, infinite, but torsion. So in fact, it's a 2 group. So every element in this group has order a power of 2. Most remarkably, probably, is that it has intermediate word growth. And let me say, all these things that I'm writing down here, we will either prove all of them or at least define and sketch some proof of all of these results. So it has intermediate word growth. In fact, it was the first group known to have intermediate word growth. It's amenable, but not elementary amenable. Let's see, can I fit everything else here? So it's also commensurable to its own direct product. All right, which is somewhat remarkable given that it's finitely generated. And the last property that we're going to talk about throughout this course is that it gives an example of a just infinite group. And in fact, its structure ends up being sort of important in the classification of just infinite groups. All right, so yeah, so sort of the main goals for the lecture is we're going to be talking about these various properties in the 4 lectures. So for instance, today we'll talk about solvable word problem, this torsion, and we'll at least start the discussion of intermediate word growth. These other properties we'll save for later lectures. But sort of the outline of the talk, let's see. Whoops. There you go. We'll figure these boards out. Yeah, 7 boards is a lot of boards. All right, so yeah, so this is the one. Yes, okay. All right, so yeah, so now let's sort of outline the talks. So part 1, which will encompass today's lecture and probably a good portion of tomorrow's lecture, will be really focused in on introducing the Gregorczyk group, defining it fully, right? Talking about, as I said, some of these properties, solvable word problem, torsion, growth. And then the other parts of the course will be dedicated to generalizing this example to other classes that have various properties in common. All right, so part 2 will be dedicated to self-similar groups. Part 3 will look at a subclass of self-similar groups, namely automata groups. And part 4 will be dedicated to branch groups. All right, so self-similar and automata groups are both groups that are going to have generators that are defined very much in the way we define the Gregorczyk group. And so it's going to let us have a lot of the same algorithmic properties that we like about this group. Branch groups, on the other hand, when we define that later, these are going to be the groups whose subgroup structure looks similar to that of the Gregorczyk group. And in particular, I hope to argue for you that trees are the right objects for branch groups to act on. Like, these are the groups that are like designed for trees, yeah? And so that's what we'll do sort of at the end of the course. All right, so let's go ahead and start defining the things we need to define the Gregorczyk group. We're going to set a little bit of notation. The notation. So I'm just going to take x always to be the number 0 up through d minus 1. I'll take x star to be finite words over x. I'll take x omega to be infinite words over x. And our reason for doing this is this gives us the notation we need to work with our trees. So x star has the structure of the vertex set of a tree. So the picture to have in mind, right, and usually most of our examples, I'll actually draw binary trees. So if x equals 0, 1, then the empty word gives my root. I have words of length 1 giving my first level of the tree. length 2, 0, 0, 0, 1, 1, 0, 1, 1, and so on and so forth. Yeah, so this is the picture to have in mind with these things. So I may have been a tiny bit misleading with my title. I said I was going to talk about Cantor sets. I'm probably not actually going to talk very much about Cantor sets, except to mention that the boundary of the tree here, boundary of tree, is naturally a Cantor space, right? Because it's exactly x omega here, these infinite sequences, yeah, of zeros and ones. So if you so choose, which can be useful but will not be terribly useful to us in this course, you can think about all these groups that we have acting on the tree as actually acting on the boundary, which gives us Cantor set action. And this is a useful perspective in many situations, but we probably just won't focus on it as much as I thought when I submitted my title 3 months ago. All right, so here's our setup. Here's our trees, our rooted trees. So let's talk about now automorphisms of rooted trees and what they look like. Let's see, frontboard. Okay. T. So yeah, so, you know, we're going to be interested in groups acting on this. So when we talk about T, this is going to be our bijections from X star to X star that, 1, preserve edge incidences, and 2, fix the root. All right. The savvy observer will notice that part 1 implies part 2, because if you look at the tree that I've drawn there, right, my root has degree 2. Every other vertex has valency 3, yeah? But I'm including this because even though I'm only going to talk about these regular rooted trees, one can define many of the things I'm talking about for something called spherically homogeneous trees. All right, so definitions can be extended often, not every definition I give in the course, but often, and it should be fairly clear when, often can be extended to what we call spherically homogeneous trees. All right, these are just the trees where the distance from the root determines the valency. So the valency can change as you move down the tree, but if they're on the same level, they have the same valency. All right, and so when you're working with that type of tree, you actually need this extra fix the root bit, yeah? All right, so working with spherically homogeneous trees, notation is significantly more complicated and not that much extra is gained, so hence why I'm going to focus on these regular rooted trees. All right, so then, all right, we can think about some consequences of this definition. So yeah, the one we saw is that the root's fixed, even if we don't assume that. Secondly, right, what this says, if we're preserving when 2 vertices share an edge and we're fixing the root, this says that if 2 vertices share a prefix, their image under an automorphism will also share a prefix of the same length. We can sort of see that by also sort of looking at what these automorphisms are going to look like. So let's describe, so to describe some G and T, there's a number of ways you can go about doing this, but what we can start thinking about is the fact that since the root is fixed, what that means is for these 2 vertices, for instance, right, the only thing that we can do is we can either fix them or we can swap them, yeah? And so if we want to, you know, make a decision for which we want to do, say we want to swap them, we just add a little permutation labeling there telling me swap these 2 vertices. But then, of course, if I swap these 2 vertices, it's going to drag this tree below it along with it, yeah? Because we're preserving this edge adjacency, so if this vertex moves over here, these 2 vertices are going to have to get mapped to these 2. Right, so this permutation tells me not only am I swapping these 2 vertices, but I'm swapping that whole tree. And then we make our next decision. We look at the next level of the tree. Again, we decide, do I want to swap? Do I not want to swap? So maybe we swap these, maybe we leave these alone. And by the time we're done, what we've done is we've basically decorated the tree. So decorated the tree T with permutations. Right? Now, we can observe, though, that I can sort of zoom in and focus on a smaller part of this picture. So for instance, I can sort of zoom in right here on this subtree. And what I see is another rooted infinite binary tree that's been decorated by permutations. And so what we're going to do then is we're going to observe that I can describe G. So describe G with G being given by some permutation. So this is going to be some element in the symmetric group on D letters, and a new set of automorphisms. So G0 through GD minus 1, where this is a new set of automorphisms. So in this picture, for instance, I have these two subtrees rooted at this level, and this is giving me two new automorphisms. And the permutation that I have here then is this permutation telling me what to do at the first level. And what this does for us is this gives us a way of sort of breaking apart our automorphisms into pieces that maybe or may not be more tractable and easy for us to understand. And so what this is really doing here when we do this is this is giving us, I want to write. So this gives us, so this is defining an isomorphism between T and, let's see, T times T, D times semi-direct product with the symmetric group on D letters. And so this tells you then how multiplication will work in this group. We'll do a concrete example in a moment. The action here is to permute these coordinates around. And so if you're familiar with wreath products, what we're really saying is that T is naturally isomorphic to the wreath product of the symmetric group on D letters with T itself. And so this is what we're going to be taking advantage of here. All right, let's do an example where we see how to actually multiply things in the semi-direct product. Let's see, let's leave this up. All right, so just so that you're a little familiar with the way multiplication is going to work with these decompositions. All right, so let's take X to be the ternary alphabet, 0, 1, and 2. Maybe I'll take sigma to be 0, 1. We take tau to be the permutation 0, 2. And then we can look at something that we've decomposed, say, as the identity in, say, A sigma, and the identity and maybe something that we'll call B identity, and then tau. So the way you multiply things in this group is I want to, slide this permutation across. And the cost of sliding the permutation across is that I have to permute these coordinates according to sigma. So what this is going to be is I'm going to have identity A, and then this says I should swap the 0 and 1 coordinate. So I get B, identity, and then sigma times tau. And now I can just think about these as being in a direct product and multiply coordinate-wise. So multiplication here is just going to be identity, or no, B in my first coordinate, identity, and A, and then the permutation that I get by multiplying sigma and tau. Yeah? Is this clear to everybody? All right, good. I'm going to give you some exercises, so that's why I want to actually show you a multiplication so that you can think about these things. All right, so now we have everything we need to define the Gregorchik group, so let's do it. All right, so what we want to do now is define and again, I'm going to reserve the notation gamma for this group. So it acts on the binary tree, so my alphabet here is 0 and 1. And it's got 4 generators that we're going to define recursively. So so first let me say I'll take sigma here to be, again, the permutation 0, 1. And then A is the identity sigma. B is AC, and no permutation at the top, and so it's kind of traditional to just leave that off. C is A comma D, again, no permutation at the top. And D is the identity in B. All right, so let's trace out. So this definition often on first glance is something that's a little unclear, right? But we can trace these out and see exactly what they're going to do in terms of a permutation labeling. So we're going to do some of these. So A, for instance, on my binary tree, A says I should do the swap at the top and then nothing else. So this is it, right? This is A, yeah? We're done, yeah? We can, draw the rest of my tree, but, nothing else is going to happen after that. B, on the other hand, so we'll start drawing the tree out here. B says I shouldn't do anything at the top, but then I should act as A on the left subtree and C on the right. So I'm going to remove my B and label the left subtree by A, the right by C. And we go back to our list and see what this says to do. So A says I should do a swap and nothing else, so I can erase my A label and put a swap right there. And now I'm done on this side, because that's A is done, right? Whereas on the right subtree, I go back to my list. C says do nothing at the top, but then act as A on the left subtree and D on the right. So I get A and D. Again, we know what A says to do, right? It's a swap and nothing more, so we get a little swap right here. D, on the other hand, does nothing at the top, then is the identity and B. And now we're kind of back at the top of our list, right? B was where we started. We're now back at B. So now we see what's going to happen. We're just going to iterate, this series of permutations following this right infinite ray. So what you'll see here, is we'll have another swap right here. We'll have another level that looks like that, right? And you just keep going. You'll see swap, swap, no swap, 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 no swap. And all right, similarly, C, on the other hand, if you start, following this right infinite ray, what you'll see is this permutation sigma, then the identity sigma, sigma, the identity sigma following this ray, and D, last but not least, right? D is going to look like the identity sigma, sigma, identity, et cetera, et cetera. Okay. Actually, before I put this up, I have not actually defined the Gregorchik group. So the Gregorchik group is just the group generated by A, B, C, and D. Yeah. Here. That's it, right? We have defined the Gregorchik group. Yeah. All right. We're going to make a bunch of observations here, though. Let's see. See if I can get everything in sight. Okay. All right. Observations. All right, the first thing I want you to observe is that each of these generators has order 2. So 1 is equal to a squared, is equal to b squared, is equal to c squared, is equal to d squared. All right, so what's happening here, if you notice, right, none of these permutations are actually lying, you know, on an ascendant of any of the others. So these permutations, the way we've drawn them here, they don't interfere with each other when you multiply things. Yeah, you're just going to be multiplying those permutations out. And since, you know, sigma is the 0-1 swap, it's just going to get killed everywhere. So this is observation 1. Observation 2 is that BC equals D, which also equals CB. So what that means then is these 3 elements, C, B, C, and D, are just going to generate for us a Klein 4 group. Yeah. So again, this is just because none of these permutations are sort of going to be interfering with any of the others in this case, right? If you have a permutation that's on some path to the root above your permutation, then you get some interaction. But here we don't, so these are all independent. We can multiply them. And so, I mean, one thing that this means, though, is we have a kind of a redundant generator here, yeah? We actually don't need all 4 of these generators, but this gives kind of the nicer presentation of the group. So it's standard to take all 4. But you can think, if you want, about this group being a 3-generated group. All right, a consequence, though, of these 2 things, which makes life a lot easier for us, is we have sort of a canonical form for elements in the group. So every non-trivial element can be written as A star B, or A star A star A star A, where these stars are in the set B, C, and D. All right, and maybe we don't need the beginning and ending A, depending on the word. But the point is here is that every non-trivial element can be written as alternating between A and either B, C, and D. Yeah. Right, so this saves us a lot of time when we're looking at these things, and it gives us kind of this nice way of looking at these. All right, so let's see. It is not unique, unfortunately. No. Right, if it was unique, then I think we would be able to conclude that what we have here is a free product, but we don't. In fact, this group is not finitely presented, which is something I won't prove, but can be proved using the same types of things we'll talk about today. I might be wrong, but I think uniqueness would imply free product. All right, so what I want to talk about is sort of a key lemma that's used in many of the things that we need here. But for us to do that, let's talk about the length of words in a group. So this is sort of going to be a broad definition. Given a group G, with finite, let's say symmetric generating set G or S, we can define let's see, for each little g in my group G, we'll define the length of G to be the min such that the min A such that S1 Sk is equal to G with Si in my generating set S. All right, so we're just looking for the shortest way that we can express my element in terms of my generating set. All right, and so then, yeah, so you can define this for any finitely generated group. So then, let's see. Here. Why is this? It's abelian on 2 generators, yeah, and each has order 2, yeah. Yeah, maybe you don't need symmetric. Yeah, probably you don't need symmetric here. Yeah. Sometimes that's just the default assumption with it. But I think we don't need symmetric here. Oh, yeah, right, of course. Yeah. So, right. So if I don't use symmetric, then I need to include, yeah, thank you. Then I need to include inverses here. So yeah, you're right. That's, yeah. Yeah, it's there, yeah. All right, so sort of like one of the most important properties the Guerrero group has is something like super straightforward that implies like 2/3 of the properties on this list can be proved using the following fact. So lemma, so let G be in the Guerrero group. Then let's say with G, when we do this wreath product, we get G0, G1, and say epsilon. Then the length of G, the length of G sub I is going to be less than or equal to the length of G plus 1 divided by 2. All right, so what this tells us is that when I do these decompositions, my words get a lot shorter in my generating set. Okay. So proof by example and full proof left as an exercise. So let's look at, all right, so the idea here is if I look at ACA, for instance, right, ACA, since A has order 2, this is the same as writing C conjugated by A. All right, but A is just an order 2 swap. So what it's going to do is it's going to take my generator, where is it? A comma C, and it's just going to switch the order of the coordinates. So this just gives me ACA, gives me, for instance, DB. Okay? And similarly for the other generators, right? Like ABA, which is probably what I should have started with here, gives me CA, and ADA just switches the order of B and the identity. Okay, this is what happens here. And so now let's look at some word of length 4, right? We said we know it has to just be some alternating product of A's and B, C, or D's. So we can work with really any of them here. Well, what I have here is C conjugated by A times B. C conjugated by A is DB. B is AC. And now I just multiply the coordinates. C conjugated by A is D. No, I have this wrong here. C conjugated by A is swapping my 2 C coordinates, so that's C is D A. Yeah? All right, so what I get here is D A times AC, which just gives me DAAC. Yeah? So I took something of length 4. I recognize that I can pair these up as conjugates of an element, times elements. And each one then goes by, we cut the length in half at each step. Yeah? So foolproof exercise. But this is the basic idea, yeah? It's just a little induction argument here, yeah? All right. So this property of the fact that these things are getting shorter, we give a name to this. See if I can get that top word down now. Oh, no. We'll keep trying. All right, so this property, I'm not going to give a formal definition, just the name here, really. We call this property contracting. All right, so we say gamma is a contracting group with nucleus given by 1, A, B, C, and D. Because if you if you iterate this procedure and you keep iterating the wreath product, we eventually get down to just single letter things. Yeah. Definition. Yes. That's algae. Yeah. I'm being sloppy with notation. Thank you. Yeah, thanks. I hope that wasn't confusing to everybody. Yeah, thanks. That should be algae. Yeah. And we have the same word length function because the states, these elements G0 and G1, they're written in terms of the same generating set. Yeah. All right, are there any other questions? They're okay so far. All right, so we'll call this property contracting. We say the nucleus is the identity A, B, C, and D because if we reiterate this wreath product on these new things here, it'll keep getting shorter as we move down the tree. Yeah. All right, and I claim this is like the main tool, underlying several of the properties on this list. So let's talk about a few of them. So let's prove it has a solvable word problem now. All right, this board. All right, gamma has solvable word problem. And in fact, a quite quick solvable word problem. All right, so the word problem goes as follows. So let W be one of these alternating words. In A and B, C, D. Then question 1, the first thing we ask is there an even number of A's? All right, because if the answer is no, right, then that means the permutation at the top is non-trivial. Right? Because the only permutation, the only thing that has a permutation at the top is A. So if the answer is no, then W does not equal the identity. Right? We're done. Yeah. If the answer is yes, decompose W as W0, W1, and I don't need a permutation here because I'm saying A shows up an even number of times, and then apply the algorithm to W0 and W1. Right. And W0 and W1 have a shorter length, so this procedure ends quickly, yeah? Because at each step, we're halving the length of my word. And that's it, right? Solvable word problem. Yeah, so what I mean is I'm going to be decomposing it in the wreath product as I did over there. Yeah, exactly, as I did over there. Yeah, exactly like this. Right, there's nothing, even this word here, we haven't actually shown it's non-trivial, right? But this, yeah, that would be a perfect example. Yes?
Contracting property depending on the nuclei.
No, so I mean, you can define lots of different, no. So they're contracting, oh yeah, repeat the question. Right, the question was, does the contracting properly depend on the nucleus? No, it's more the other way. The nucleus depends on the grouping contracting, yeah? So you can talk, which we will more generally when we talk about automata groups that are defined in this way with recursive generators. And you can say, you know, if the words are getting shorter, we say the group is contracting. And then the set of words we reduce to is the nucleus. Yeah. So yeah, I can repeat that definition maybe on Wednesday when we have the more general setup. Yeah. So nucleus, yeah, is just more about the fact that the words get shorter. And we define this. All right, what else? Let's see. Okay, so all right, let's talk about torsion, yeah? Yes, please. Yes. Yeah, right. So it could be actually smaller than the generating set. It depends on what things show up as in the decompositions. Yeah. So it's not always the true case that, yeah, I mean, we'll define these groups more generally where maybe I should give some language here at the moment. So like this dA, for instance, these two elements, we give the name that these things are the states of the element. So in later lectures, we'll define a self-similar group as groups where the states are back in the original group, right? And so from that, then you can talk about things like this contracting. Yeah. Yes? Yes. Yes. Yes, yes, that's what I'm saying, right? Like a lot of these properties are near direct consequences of this, if not immediate consequences of this. And in fact, there is another algorithm that doesn't require this. It's just not going to be as fast. And we'll talk about that again when we get to automata group. Yeah. Any other questions? Yeah. I should have repeated your question. Yeah, so the question was about, the fact that the proof of this is really the proof of this. Yeah. All right, so let's talk about torsion. So torsion. So another fact is that every element of gamma has order power of 2. All right, so this one I'm going to be sweeping a little bit more under the rug. The proof requires a little bit of case-by-case analysis of different types of words, looking at odd-length words and even-length words. But the picture to have in mind is let's look at a specific example. So let's look at the element AB, and I claim AB has order 16. So more what I'm going to show you is how to actually verify that this has this order. So AB has order 16, and the way, you know, we can see this is, again, writing this as AB, AB, AB a bunch of times here, and then seeing that this is B to the A, B, B to the A, B. Okay. Just again, because A and A inverse are the same thing. Yeah. So what I have here is really B conjugated by A, B, B conjugated by A. And then I use, you know, this, right? That B conjugated by A just switches the order. And so now we like start drawing our tree, yeah? Maybe I should do this somewhere I have more space. All right. So I draw my tree. I have AB to the 16th. All right, and what I'm going to see when I, you know, iterate this sort of back and forth here, what I get is on the left, I'm going to get CA to the 8th and AC to the 8th. But then I repeat the procedure, yeah? So AC, ACA is just C conjugated by A times C, C conjugated by A times C, yeah? And so that's going to leave me with AD to the 4th, DA to the 4th, DA to the 4th, and AD to the 4th. I do this again. All right, so now I have d conjugated by a bunch of times here, and that's going to leave me with b squared, b squared, b squared, b squared, b squared, everywhere, yeah, b squared. And b squared's the identity, yeah. So what we see here is we never saw any permutations along the way, and as our words got shorter, we eventually ended with a bunch of stuff that equals 1. Yeah. And so, you know, you sort of do this case-by-case analysis where you look at words of a certain length, you know, you take these powers and you do some inductive stuff, yeah. And this is how it works. But again, like you can sort of see that a lot of what's going on is really, you know, coming from this contracting property. But yeah, the general proof is really case checking. All right, so we've checked 2 things off the list, right? We've seen it's got solvable word problem. We've seen it's finitely generated in torsion. I didn't actually prove it's infinite, but maybe you can believe me that it's infinite. Yeah. Yes, yes, this one is 16 on the nose, yeah. Yeah, no, just, I mean, you could do it because all you have to do is keep squaring till like, you know, you repeat this procedure squaring and then do it again, yeah, and then you'd be able to see immediately the length, right? So like you're just looking for permutations. If you see some non-trivial permutation, you have to square your element, yeah, like this is kind of ridiculous. Yeah. All right. Let's see, what else is on our list? All right, so I think we're ready to talk about word growth, yeah? So let's do that. Let's start on a new board. Here. All right, word growth. All right, so this is probably the thing that the Gregoric group is most known for, the fact that it gave this first group of intermediate word growth. And even still today, like there's, you know, we'll talk at the end about some recent results still coming out in this area, but they're almost always using the Gregoric group as sort of like the starting point, and, you know, even these 40 years later, right? So let's talk about what we mean by word growth. So definition, some definitions here. So again, we're going to fix a group G with generating set. And yeah, we do need symmetric here, I guess. Symmetric generating set. S. And then we can talk about the ball of radius k. So the ball of radius k and g is the set of elements g and g such that this length function we defined earlier is at most k. So we're just looking at now all elements in the group of length at most k. And then we can define the growth function for g is the function, which I'll call beta sub g of k, which is just the size of this ball of radius k. All right. So in other words, what we're doing is we're counting, you know, these elements in the ball of radius k. As k grows, right, we get different beta values. But this is a non-decreasing function. As stated, it currently depends on our generating set, but we can make it not depend on our generating set by looking at equivalence classes of functions. All right, so now we say two non-decreasing functions say f and g. Okay, so let's say for two non-decreasing functions f and g, say that f is asymptotically less than g if there exists a constant c greater than 1, greater than or equal to 1, such that f of k is less than or equal to c g of ck for all k. Okay, greater than or equal to 0. All right, and then we'll say that two functions, so say f is equivalent to g if f is both asymptotically less than g and g is asymptotically less than f. F and g, yeah, positive. Non-negative, yeah, sure, yeah. So, I mean, they're non-decreasing, and they're, let's say, they're functions from f and g, functions from 0 to infinity to r, or to r is good enough. And since they're non-decreasing, I think, then they have a lowest element, and we're good, Yeah, okay. So, right, this gives us an equivalence relation on growth functions in particular, because these are non-decreasing functions. They have the smallest value, 0 to infinity here. And so what this means is if we consider this growth function beta g of k up to equivalence, it no longer depends on the generating set. So that's what we'll do, right? When we talk about growth functions, we'll really talk about it as setting in this equivalence class. All right. Yeah, so, right. Can I do this in a way that this stays visible? Okay. One at a time, yeah, okay. Thank you. Yeah. Okay. All right, so when we start talking about these growth functions, then, we want to know what types of functions can actually occur as growth functions of a group. So really this starts with Gromov's polynomial growth theorem. All right, which says a group G has polynomial word growth if and only if it is virtually nilpotent. All right, so this is one of these places where we see, right, these properties of the Cayley graph, right, are pretty intimately connected with the algebra of the group, yeah? And so this was a hugely important theorem when Gromov proved this. But, on the other hand, so this gives us our first growth functions that can occur, these polynomial ones. It's quite easy to give groups of exponential growth Can anyone give me a group of exponential growth? What is it? Yeah, say it again. Free group, right? Free group. Yeah, groups of exponential growth. Thank you. Yeah, thanks for your participation. Groups of exponential word growth? Yeah, lots of things, but free groups, you know, for instance. Right, their Cayley graph is a tree, right? And you're counting vertices in a tree farther and farther away from the origin. All right, but it was open for a long time whether or not these were the only two options. So it was open for a long time whether the only options were polynomial or exponential. So it was officially asked by Milner in '68. So Milner, 1968, asks explicitly about the existence of groups of intermediate growth. So when we say intermediate growth, what we mean here is we mean strictly faster than any polynomial and strictly slower than any exponential function. And, you know, by our list of properties here, our group gamma has intermediate growth. So gamma gives, and that gave the first example. And this is really remarkable, right? It took, quite a long time for people to come up with this example, for Grorczyk to come up with this example. So if we want to prove, which we will, we're going to sketch the proof of this subject to a couple of key technical lemmas that I hope you're willing to accept without me writing the proofs of them. But really, we have two things we need to prove here, right? If we want to prove that this has intermediate growth, we need to prove the growth is not polynomial. And we need to prove the growth is strictly less than exponential. Right? So let's start by proving that it has growth that's not polynomial. So polynomial is the lower bound, right? Nothing has growth lower than polynomial. All right. All right, and our proof is just going to follow from Gromov's polynomial growth theorem. Right, we just have to prove it's not virtually nilpotent. Yeah. All right, I give up on that word, but that's okay. You can see most of what's up there, yeah? All right. All right. All right, theorem. Gamma has super polynomial growth. All right, proof. There's really two proofs you can do here. So the first is going to use Gromov's polynomial theorem. So suppose not, right? Suppose it has polynomial growth. By Gromov's theorem, we have a finite index nilpotent subgroup. Has a finite index nilpotent subgroup. All right, but gamma is a torsion group, yeah? Well, let me name my subgroup. Let's call it H. So gamma torsion implies H is torsion. But if you know something about nilpotent groups, torsion nilpotent groups are finite. Let's see, I might need finitely generated here, but we do have finitely generated because it's finite index in a finitely generated group. But anyway, so torsion, yeah, finitely generated. Nilpotent groups are finite. And I mean, that's our contradiction, right? Because that would imply gamma is finite, but it's not, right? I mean, I haven't proved to you that it's infinite, but, you know, gamma is finite, which is our contradiction. That's it. That's all we really need. All right, but, you know, maybe you say Gromov's theorem is a pretty big hammer. So if you want to avoid Gromov's theorem, you can. You don't really need it here. So let me just say a couple of ideas about a proof that uses, you know, a mallet instead of a sledgehammer. So an alternative proof that one can do. So alternative proof, which I'm not going to give all the details here, but the idea here is to show any group G commensurable with its own direct product with G cross G cannot have polynomial growth. All right, so I haven't defined commensurable or any of this stuff, so that's why I'm also giving you this proof here. But we'll talk about commensurable and what it means to be commensurable with your own direct product when we talk in the branch group section. Yeah, that's when that will come up. All right, so we still have a few minutes, yeah? So 10, okay, cool. So let's start in on some of the ideas that we're going to need on sub-exponential growth. Maybe we'll finish here. Let's see. All right, so yeah, so our next thing to prove is sub-exponential growth. All right, I'm going to try this board again. Let's see. Yes. I think sometimes they just need a rest, yeah. All right. All right, so we now need to show that gamma has sub-exponential growth. And yeah, this proof is going to rely on a couple of technical lemmas, some counting type arguments. So the first lemma, so lemma 1, is going to be a lot like this contracting thing, except it's slightly stronger. So this is something kind of specific to the Gregorczyk group. So suppose that we have some element in the Gregorczyk group which stabilizes pointwise here, the third level of the tree. All right, so what that means, right? When we draw our picture, it means we have no permutations showing up before we hit the third level. Yeah, this is the first place anything shows up. And so what that means is, you know, we can, again, iterate this sort of wreath recursion, this wreath product. And what we're going to get is we're just going to get a bunch of automorphisms here. on each one of these trees, right? We're going to have we're going to have some labels, eight different labels showing up here, yeah? So what we're going to do is let Gij, Jk, where I, j, and k range over the set 0 and 1, be the set of states of G on the third level. So again, I haven't really given formally this definition of this word state, but all I mean is, right, we're going to have some automorphism here, like G0, 0, 0, G0, 0, 1, you know, et cetera, all the way down to G1, 1, 1. Right? We're going to have these 8 different labels on these 8 different subtrees here. And they're all going to be words in A, B, C, and D. Yeah? All right, so we have these. So then, if I take the length, if I sum up the length, so sum over I, j, and k of the length of G, I, j, k, if I sum up the lengths of each one of those words, this is less than or equal to 3/4 times the length of G plus 8. So you can think about this as a lot being similar to this contracting property, but it's a bit stronger, right? So it's not just saying that individual pieces get smaller, but in fact, if I sum up all the lengths of the individual pieces, it's still getting shorter. Right? All right, so we're not going to prove this technical lemma. It does take a little bit of work to prove it, but it's, you know, it's just working with elements of the group. All right, the second lemma we need is just, again, it's a counting lemma that's true for groups in general. So lemma, let G be a group. And let G be a group with finite generating set S. With finite generating set S, and you know, as before, we'll take B gamma of, or B G of K to be the growth function. Growth function of G with respect to S. All right, and now let's take. So let's let G naught be a subgroup of index n. In G, and we're going to define then another function. So B naught or beta naught of K. And so what we're going to be doing here now is just summing the elements in the finite index subgroup. So this is going to be the size of the set of elements G and G naught, such that the length of G with respect to the same generating set is less than or equal to K. Okay. So we're just taking the ball of radius K and we're intersecting it with the finite index subgroup. That's all this says right now. Yeah. So we're taking the size of intersection of ball of radius K with this finite index subgroup G naught. All right, and now we're going to bound beta using beta naught, basically here. So then if you apply some counting arguments, you get that beta sub G of K is going to be less than or equal to n being the index here, right? N. n times theta naught of k plus n minus 1. Thanks. All right, so there's just a few minutes left, so I'm not going to complete the proof of sub-exponential growth today. So let me just say one more fact and give you a preview for what we'll do at the beginning next time. So what we're going to do, maybe not surprisingly, is we're going to take, G to be gamma in this lemma. We'll take the stabilizer and gamma of the third level to be our G naught. And then one can check here that this has index 2 to the 7th in gamma. And I mean, it's just, it's maybe, you could do it by hand. It's a little bit of maybe a painful permutations group calculation by hand, but you could run it through GAP, right? There's lots of stuff in GAP just to say, like, type in these permutations and figure out the size of my permutation group. All right, so yeah, the idea here now then is we're going to be playing these inequalities off of each other, right? So one, we have this finite index subgroup that we can use to bound my growth function in terms of the finite index subgroup. But then we're going to use this inequality to, do this counting argument the other way, and these, and we're going to play these things off of each other. So, yeah, with just 2 minutes left, I'm not going to start the proof of sub-exponential growth, but next time I'll remind you of these two lemmas, and we'll complete the proof. But it's just a little bit of back and forth. Thank you.